Actually, let me recap the whole thing for you. So given a matrix A, okay, the non-zero rows of the REF of A form themselves a basis for row A. All we had to do is start from the matrix, put it in our REF form, look at the non-zero rows, they are a basis for the row space. On the other hand, the columns of A in pivotal positions, remember, those are the ones which are going to be independent. The ones that don't have pivots, that means that they're going to be dependent on the others. They will form a basis for the column of A. Probably it's a lot better if I give an example. Okay, so here's the example. Consider this matrix. Okay, you may want to put that matrix in your calculator, find out what the REF is, and remember, you're probably going to find a different REF from the one I'm going to show you. Okay, but the REF I came up with is this one. So let's say that what I want to do is I want to find a basis for row A. So all I have to do is look at the rows in the REF of A which are non-zero. So that would be the first two rows. Well, they form a basis for the row space of A. Remember, they are linear combinations of the original rows, so they're still in the same space, and they're independent because again, they're not multiples of each other, and they're the only two that we need because the last one became 0, which means that the third row is not really needed. Okay, so as far as the basis for the row space of A is concerned, that's all we need to do. Now, for the column space, however, things are a little bit different. Again, remember, by doing row operations, we have changed the columns and we have sent them outside of the column space. However, the relation of dependence is still the same. So what we do is we look at the columns in the REF that have pivots. So the first and the second column have pivots, 2 and 7 respectively. That means that those two are independent, definitely. The other two, however, are going to be linear combinations of the others. Okay? You want to double check that it is true. In fact, it's enough to double check that the first two numbers are dependent, right? The vector consisting of just the first two entries, because the last ones are all 0 anyway. And of course, the first two columns give us two vectors. We only need to worry about two components, so we know that we have enough to span the rest of it. So what we're going to do, but those are not the columns we want. Remember, we may have gone totally outside of the column space. What we want to do is go back to the original matrix and find the two corresponding columns. We had the first two columns had pivots in them, so we'll look at the first two columns in the original matrix. Those two will always turn out to be independent, and they are enough. They provide us a basis for the column space of A. Again, this is something I realize when it comes to figuring out these bases for the column of A, that it's not very intuitive. It requires a little bit of thinking and perhaps a little bit of practice in playing with these things and checking. For instance, check in this case that 532 is in fact, that's the third column of the original matrix, that is in fact a linear combination of the first two, and so is 202, which is the last column. So we don't need those two. The first two are enough. The method we just saw, or the methods we just saw to identify a basis for the column space and one for the row space are linked to each other in a very interesting way. Namely, first of all, notice that a basis for the column space of A has one vector for each pivot, right? That's how we found them. We identify the pivots, go back to the original variable, pick up the corresponding columns. But on the other hand, the same is true for the row space, because of course each non-zero row will have one pivot at the beginning, okay? And therefore, the number of elements in a basis for the row space and the number of elements in the basis for the column space of the matrix are the same. So that means, therefore, that the dimension of the column space of A is equal to the dimension of the row space of A. Okay, and of course that means in particular that and this is what we originally called the rank of A. So the rank of A, remember, was the number of non-zero, or the number of pivots in the REF of the matrix. So this turns out to be the same as the dimension of the column space or the dimension of the row space. Okay. Now, another consequence of this fact is because, of course, row and column simply interchange when we're transposing things. That means that the rank of a matrix is equal to the rank of its transpose. Now this is something probably we have seen in the past, but in this case it becomes fairly obvious. Basically, even though we're doing row operations both on the rows and on the columns, both on A and, well, not on transpose of A, basically on transpose of A we're not doing row operations, we're doing column operations, but basically turns out that the result is still the same and the ranks are the same.